All right, section 5.1, Fundamental Identities, starting on page 115 of your notes packets. The first identities that I'm going to define are called the reciprocal identities, and you should be a little bit familiar with these. We'll start with cosecant of theta, which is 1 divided by sine of theta. Now, if sine is the reciprocal of cosecant, then cosecant is the reciprocal of sine, so we can also say that sine of theta equals 1 divided by cosecant of theta. That's our first pair of reciprocal identities. Next, we can look at secant of theta, which can be defined as 1 divided by cosine of theta. And then we can also say that cosine of theta is 1 divided by secant of theta. And our last pair of reciprocal identities is cotangent of theta, defined as 1 divided by tangent of theta. And similarly, we can say that tangent of theta is the same as 1 divided by cotangent of theta. Next, we'll look at quotient identities, quotient meaning division. So notice reciprocal means 1 divided by something. Here, we'll have a numerator that's non-1. So our first quotient identity is that tangent of theta equals sine of theta divided by cosine of theta. And our second quotient identity is that cotangent of theta equals, using the idea that tangent and cotangent are reciprocals, cotangent of theta could also be defined as cosine of theta divided by sine of theta. Notice here again, tangent and cotangent are reciprocals. All right, the next set of identities that we'll talk about are the Pythagorean identities. Now this is where the most complicated identities come from. We start with the idea that cosine squared of theta plus sine squared of theta equals 1. Now this comes directly from the unit circle. If you think back, our radius was always 1, and sine and cosine were essentially our x and y values. So if you take the Pythagorean theorem, which was that the legs squared equals the hypotenuse squared, we'll get this identity that cosine squared plus sine squared equals 1. This notation, cosine squared of theta, means the value of cosine of theta squared. Okay? From here, if we divide each term by cosine squared of theta, we could get 1 plus tangent squared theta equals secant squared theta. And similarly, if we take our original identity and divide everything by sine squared of theta, we'll find the identity that cotangent squared theta plus 1 equals cosecant squared theta. So these are the first three of the Pythagorean identities. Now let's see how we put these into use. So in example 1, we're looking for sine of theta and cosine of theta. We are given that tangent of theta is 5 and that cosine of theta is positive. So starting with the idea that tangent of theta is 5, we know that from here, secant squared of theta is 1 plus tangent squared of theta. So let's start with secant squared theta equals 1 plus tangent squared theta, which is 1 plus 5 squared. So I've substituted in the value for tangent. So that's 1 plus 25, which is 26. So I know that secant squared theta is 26, then secant of theta has to be plus or minus the square root of 26. So if secant of theta is plus or minus the square root of 26, then I can find the reciprocal of secant, which is cosine of theta, which is defined as 1 over secant of theta, would be 1 divided by plus or minus the square root of 26. We also know that cosine is positive, so we can eliminate the negative option here, and we say cosine of theta has to be greater than 0. So cosine of theta equals 1 over the square root of 26. Now we still need to find sine of theta. So we can go back to the idea tangent of theta is 5. And that is sine of theta divided by cosine of theta. Substituting in this value for cosine of theta, I can say 5 equals sine of theta over 1 times 1 over 1 divided by the square root of 26. Let me fix the framing here. So that's sine of theta times the square root of 26, dividing both sides by the square root of 26. I find that sine of theta equals 5 divided by the square root of 26. All right, so our final answer, cosine of theta is 1 divided by the square root of 26, and sine of theta is 5 divided by the square root of 26. The next set of identities that we'll look at are cofunction identities. Cofunctions are sine and cosine, tangent and cotangent, secant and cosecant. So we're looking at relating those types of functions, those pairs. We'll start by saying sine of pi over 2 minus theta equals cosine of theta. Similarly, we can say that cosine of pi over 2 minus theta equals sine of theta. Our next pair will look at tangent of pi over 2 minus theta equals cotangent of theta, and cotangent of pi over 2 minus theta equals tangent of theta. And then lastly, we'll say secant of pi over 2 minus theta equals cosecant of theta, and cosecant of pi over 2 minus theta equals secant of theta. Next, we'll look at odd and even identities. Recall odd functions such as x cubed, x to the 5th, have symmetry with respect to the origin, and even functions such as x squared, x to the 4th, etc., have symmetry with respect to the y-axis. So we're looking at what that does in the terms of our trigonometric functions. We have that sine of negative x equals negative sine of x, and similarly cosecant of negative x equals negative cosecant of x. We have cosine of negative x equals cosine of x, and secant of negative x equals secant of x. We have tangent of negative x equals negative tangent of x, and cotangent of negative x equals negative cotangent of x. All right, we have sine, cosecant, tangent, and cotangent, which are our odd functions, and cosine and secant, which are even functions. So all of these kind of follow the same pattern, where if the argument is negative, we can kind of pull that negative out. We can use symmetry to say that sine of negative x is equal to negative sine of x. Whereas for cosine and secant, because they are even, if we have a negative in the argument, it's the same as if the argument was positive. All right, again, applying this to an example, we're looking at example 2, simplifying this expression. The first thing I want to do is notice that there's a sine of x in both of these terms, so I'll factor it out. If I factor out sine of x times sine squared x plus cosine squared x, I can say now sine squared of x plus cosine squared of x, if you'll recall from the Pythagorean identities, is equal to 1. So I have sine of x times 1, which is just sine of x as the final answer. Similarly, for examples 3 and 4, you want to take these expressions and use the fundamental identities that we've talked about to simplify them as much as possible until you've reduced it down to an identity or to a function that cannot be reduced any further. All right, moving on to page 118, looking at example 5, find all values of x in the interval from 0 to 2 pi that solve this equation. So we're looking for one full cycle of the unit circle. What values of x make cosine cubed of x divided by sine of x equal to cotangent of x? So the first thing I'm going to do, I want to, maybe I'll write this in terms of all sine and cosine to see what I can reduce. So first we'll keep cosine cubed x divided by sine of x and rewrite cotangent of x. Cotangent of x was cosine of x divided by sine of x, so cosine of x divided by sine of x. Now I can see I have sine of x in the denominator on both sides, so I'll multiply by sine of x. So that will reduce to 1, and I'll be left with cosine cubed x equals cosine of x. Okay, now let's move all of this to one side, so I'll subtract cosine of x from both sides, and I'm left with cosine cubed x minus cosine of x equals 0. I'll factor out a cosine of x. Cosine of x times cosine squared x minus 1 equals 0. Now cosine squared x minus 1, that looks very similar to our Pythagorean identity, but notice instead of 1 minus cosine squared x, I have cosine squared x minus 1. So if you would look back at that Pythagorean identity, sine squared plus cosine squared of x equals 1. Subtracting cosine from both sides gives us the opposite of what we have here. So that means I could replace cosine of x times negative sine squared of x equals 0. All right, so I have that cosine of x is 0 or negative sine squared of x is 0. But we had sine of x in the numerator, so sine squared of x cannot ever be 0. Sine of x not equal to 0 from denominator. So our answer comes from when cosine of x is 0. Cosine of x is 0 when x equals pi over 2, 3 pi over 2. All right, for the next example, it's labeled as example 5 again. Go ahead and change that to example number 6. We want to find all of the solutions to the trigonometric equation 2 times sine squared of x plus sine of x equals 1. I immediately notice that our first sign is squared, but our second sign is not, so this reminds me of a quadratic equation. So I can use substitution and say let y equal sine of x. And then I'll rewrite this equation. So 2y squared plus y equals 1. Now solving for y, I can subtract the 1. 2y squared plus y minus 1 equals 0. Sorry about that, my camera cut out. But while it was out, all I did was factor the quadratic equation. Okay, from here, we can use the zero product property to say that 2y minus 1 equals 0, or y plus 1 equals 0. Now we want to substitute our y back to sine of x. So 2 times sine of x minus 1 equals 0, or sine of x plus 1 equals 0. Let's solve the left-hand side first. 2 times sine of x equals 1, adding 1 to both sides. So sine of x equals 1/2. Let's look where on the unit circle does sine of x equal 1/2. Well, sine of x came from our y value. So sine of x is 1/2 when our angles are theta equals pi over 6 plus 2 pi k. So no matter which rotation, if it's the first rotation or if we go all the way around and then back up, if we have pi over 6 as our reference angle in quadrant 1, or if we have 5 pi over 6 as our reference angle in quadrant 2, plus 2 pi k. Okay, how about our second side? On the right hand equation, we can subtract 1 from both sides and get that sine of x equals -1. Again, if we look at our unit circle, sine of x is 1 at theta equal 3 pi over 2 plus 2 pi k. So all together, this gives us our answers, our solutions. Technically, this is infinitely many solution because no matter what value of k we substitute, the original equation will be true. All right, take a moment to reflect on the lesson and then summarize what you learned in the box below.